Welcome to the Global Composites Experts webinar series. My name is Wenbin Yu, Director of the Composite Design and Manufacturing Hub. This webinar series is to examine the history, present capabilities, and future of composites, with the goal of sharing the knowledge of composites that has been developed over the past 50 years. This webinar series was initiated by the Composite Manufacturing and Simulation Center at Purdue University. We are located in this beautiful Indiana Manufacturing Institute. All of you are welcome to visit us when life returns to normal and it is safe for us to travel. We launched the CDM Hub in 2013 with the mission to convene and serve the global composite community by creation, education, evaluation, and sharing of resources for composite design and manufacturing. CDM Hub provides a very powerful website called cdmhub.org for the composite community to carry out this mission together. We envision CDM Hub to become the premier resource for composite design and manufacturing in the near future. This webinar series is one of the initiatives CDM Hub started as a service to the community. This webinar series is made available by the support of CDM Hub sponsors, including Dassault Systems, SciTech Solvay, MAC Software, and Modex 3D. We greatly appreciate their financial support for CDM Hub. Next, I will show a brief commercial from one of our sponsors.
The Dassault Systems 3D Experience Education Center of Excellence in Advanced Composites is the result of a 7-year partnership between Purdue University and Dassault Systems. It is expected that this new level of engagement will bring significant benefits to the two partners and to the global society as we work together to bring the advantages of the digital age to society. Together, we will advance the digital enterprise by developing the human talent essential to this new paradigm and by utilizing the 3D Experience platform to exercise digital twins of complex composites manufacturing and performance to demonstrate the power for simulation of phenomena that are understood today only by empirical experiences. We will work together to introduce those concepts to a wide range of industries within the advanced composites community, from the original equipment manufacturers to the supply chain industries.
Thanks again for our sponsors' support. We invite more organizations to join them to serve the global composite community together. This webinar will be recorded and made available on CDM Hub. An email will be sent to you once the recorded video is available online. The presentation will last about 40 minutes and will have about 15 minutes for Q&A. All attendees are muted. Please submit your questions through the Q&A box. After the speaker's presentation, your questions will be read and answered.
Welcome, everyone. My name is Dielin Zhang. I'm assistant professor of the School of Aeronautics and Astronautics at Purdue University. Today, I'm honored to have the privilege to introduce our webinar speaker, Professor Nancy Sottos. Professor Sottos holds a Mabel Leland Swanland Endowed Chair and is head of the Department of Material Science and Engineering at the University of Illinois Urbana-Champaign. She was elected to the National Academy of Engineering in 2020. Professor Sottos is the leader of the Autonomous Materials Systems Group at the Beckman Institute for Advanced Science and Technology and the director of the University of Illinois, spokesman of the Beeping International Center for Advanced Materials. She is also a co-founder of Autonomous Materials Incorporated. Inspired by autonomous function in biological systems, the Sottos Group develops polymers and composites capable of self-healing and regeneration, self-reporting, and self-protection to improve reliability and extend material lifetime. Her current research interests focus on new bio-inspired methods to manufacture these complex materials. Professor Sottos' research and teaching awards include the ONR Young Investigator Award, the Scientific American's SciM50 Award, the Hetani Best Paper Award in Experimental Mechanics, the M.M. Fraud and the B.J. Lazan Awards from the Society for Experimental Mechanics, the Daniel Drucker Eminent Faculty Award, the ICAM-E Global Research Award, and the Society of Engineering Science Medal. She is also a fellow of the Society for Experimental Mechanics and the Society for Engineering Science. Now I will give it to Professor Nancy Sottos.
Thank you, Professor Zhang, for that introduction. And it's my pleasure to present work in this seminar series that the group at Illinois has been carrying out. So I will be speaking about the control of reaction fronts this morning, and the use of that for rapid, energy-efficient manufacturing of multifunctional polymers and composites. I'm in the Department of Material Science and Engineering, but also a member of the Beckman Institute, and as we said in the introduction, part of the Autonomous Materials Systems Group. Let me just start out with some acknowledgments and a little bit about the way research is carried out at Beckman and in my group. It's highly interdisciplinary, and so the work that I'm going to show you is efforts of a lot of different people. Across the top, I show you the different students that have been involved in this research, and some are alumni at this point. But I'm going to highlight the work of Paulette Sentalis, who's a current PhD student, Nil Parikh, who's a current PhD student, a little bit on Gia's printing work, Mayank Garg, who's a current postdoc in the group, and then also highlight Dr. Leon Dean, who's now at 3M, and Mustafa Yordkani, who's now assistant professor at Colorado State, and current graduate student Doug Ivanoff. On the bottom, I show the faculty collaborators, my longtime collaborators, Jeff Moore, who is in chemistry, and Philippe Goubel, who's in aerospace engineering. And then also I want to acknowledge our colleague, Scott White, who passed away 3 years ago, but was an integral part in forming the vision for this work. And of course, I want to acknowledge the people that sponsor this work, which are the National Science Foundation through their LEAP-High program, as well as the AFOSR, which sponsors the multifunctional work, and of course the Beckman Institute and the resources that we have in the Autonomous Materials Systems Group. So moving forward, let me tell you a little bit about the way we think about this problem of composites manufacturing and our motivation. And it starts out with a common problem that manufacture of composites is expensive, and it's difficult to integrate multifunctionality, integrate different things into this because of the autoclave process. And I'll say a little bit more about that on the next slide. In addition, composite structures must function in a range of extreme environments as they go through their lifetime. And so they're subject to all sorts of damage that ultimately leads to component failure. And as a whole, my group over the years has been looking at different bio-inspired functions that can address these damage questions like self-healing and regeneration. And our goal is really to improve performance and safety. My talk today, though, is going to focus on the manufacturing aspects, and I'll say a little bit about, I'll comment on multifunctionality and vascular structures towards the end of the talk. So I think everyone on this seminar series is well aware of the challenges associated with composite manufacturing. Again, I show the large autoclave for aerospace structures, and then also show on this side one of the large molds required for creating composites for wind blades. And if we look at sort of the well-known processing cycle for many aerospace-grade thermosets, it requires, I think the first obvious element is that it requires lots of time, a minimum of 6 hours, sometimes longer. High temperatures held for those long times, usually 2 dwells. And the heating rates are low. Sometimes the curing can be non-uniform. You induce residual stresses. And those large molds and autoclaves I showed on the previous slide require large capital investment and operating expenses. And you have to have these manufacturing facilities available. And of course, there's a lot of energy in, and that leads to CO2 emission. And so really the autoclave curing process that we've used or has been used for so long to make high performance composites is labor and capital intensive, and costs increase exponentially with part size because the autoclave has to increase in size with the part that's going to go inside of it. So when we set out on this area of research, we had some goals and some challenges. And one was to reduce the time to cure of thermoset composites, and also to reduce the energy consumptions, as well as the capital investment costs, and hopefully some CO2 emissions. I'm going to comment on some of the work that we published in 2018 on our technique, but this plot is taken from there, and I'll refer to it a second time in the talk. But let me just start out with conventional curing. As I said, it's pretty energy intensive, and we made this kind of Ashby plot of energy consumed per unit volume versus the time to cure per unit volume. And you can see whether you're making a flat panel or you're trying to make a 787 fuselage, there's quite a bit of energy per unit volume. And I said it scales, the energy does scale with volume for a typical autoclave process. And our goal, and I'll mention later on, how it was to get more into this quadrant, reducing both time and energy. So an outline for the things that I'm going to cover today, I'm going to talk about a technique called frontal polymerization that we've been working on and serves as a platform for our manufacturing methods. Then talk about application to fiber reinforced composite manufacturing specifically, and then finish with an exciting application to vascular structures and using this technique to make multifunctional composites. So let's start out with some frontal polymerization, and I'll assume that many of you don't know a lot about frontal polymerization. This is a technique for processing polymers, creating polymers that has been in the literature for a while. If you're unfamiliar with it, there's a great review by John Poyman's group, and many different. It really references all the different polymers and monomers that have been polymerized using a frontal polymerization technique. But let me tell you a little bit about what frontal polymerization means. It's really like a controlled burn, but you start out with monomer. The monomer has to have a high heat of reaction. And then in that monomer, you're going to also include a thermally latent initiator. In our case, we had a catalyst. And you need to stabilize that system until, to give you enough working time. Then when you add a small amount of heat, so you can think about the heat as a trigger that's not going to remain on, it starts the polymerization of the monomer. And the monomer, as I said, needs to be fairly exothermic. It generates heat, which diffuses forward into the surrounding monomer, which again generates reaction, an exothermic reaction, which then diffuses forward, and the reaction propagates as a self-sustained front. Most of the work on frontal polymerization has been done in this highly advanced mold of a test tube, and you basically trigger it with a small amount of energy. I'm going to start the video after, basically we trigger this with a soldering iron for demonstration purposes. The soldering iron is already gone. And you can see the front start to move. This is also changing color as it polymerizes, as the monomer polymerizes. So as it goes from monomer to polymer, it's going from a pink to a yellow-orange color. And you see it just fully and smoothly propagates down until you have a full conversion of the monomer. if we look at this in an IR video, and this is an IR of a, not the same test tube, it's actually a little more zoomed too. And again, it started just after the point where it's been initiated with a soldering iron, so just a small heat trigger. And this will give you, again, a feel for how the heat is generated due to the reaction and then diffuses and propagates down the tube. So you can see red here is a hotter temperature. It starts to react. The heat starts moving forward, and the reaction front, again, smoothly moves down through the test tube, curing the monomer. Okay, and it's just about finished. All right. So if I take some snapshots of that and just freeze them on this slide, you can see again that you start out with this stable monomer, and you can see the smooth propagation of the front. And I just want to include too the governing equations for this. This is a reaction thermal transport system where T here is temperature, H of R is the heat of reaction. That's a property of the monomer. Kappa, rho, Cp are also properties of the monomer that determine the heat transport and the diffusion. And then alpha is the degree of cure. And then I show the cure kinetics for a typical thermosetting polymer here. But alpha also depends, of course, on temperature and an activation barrier, E. And so we're able to also analyze this set of governing differential equations to understand this reaction thermal transport process. Now, I won't have time to talk about the modeling this morning. That's the work of the Gubel group. But we have a lot of predictive models that enable us to hone the manufacturing processes and understand them better that I'm going to show throughout this talk. But let me start out with the chemistry that our group has been focusing on, one particular monomer. And that is the monomer is dicyclopentadiene, or DCPD for short, which you see over here. And we initiate a frontal ring opening metathesis polymerization using Grubbs catalyst, in particular GC2. And so the chemistry that we're working with is the DCPD monomer. It's endoform, a norbornene, or ENB, that is added to make this a liquid at room temperature, the Grubbs catalyst, and then I'll say some more about these inhibitors, which are incredibly important for stabilizing the systems, and one of the big advances that our team made, led by the Moore group. But what these inhibitors do in this working with this monomer is that we're able to move from the test tube from a very small volume and doing frontal polymerization on a very small scale to larger molds. And here I just show a casting mold of our dicyclopentadiene monomer. The heat trigger here is a resistive wire, and it's just on for less than a second, actually. And you can see, again, a smooth polymerization front progressing throughout the mold. And what we wind up is a thermosetting polymer, polydicyclopentadiene, by the time that all the monomer converts. And this thing is cured with just 6 joules of energy in 78 seconds on a desktop. The front velocity is about a millimeter per second that you see there. The degree of cure is quite high. But what's most remarkable to me is that the glass transition temperature of this material is 160 degrees C. It's got a Young's modulus of about 2 GPa and a good elongation of failure, about 50%. So it's got great engineering properties comparable to those of a aerospace grade thermoset. And here I just show a comparison of those properties to a typical aerospace grade BPA epoxy. And when we started out, we were very careful to compare our frontally polymerized materials to if we just cured them in a traditional oven versus our traditional oven or autoclave cure of the BPA epoxy, and looked at the modulus. The modulus of DCPD is about 2.0 compared to 2.5 of an epoxy system, and the tensile strength or yield point is rather comparable. What's also interesting, though, is that dicyclopentadiene is a very tough material. Its fracture toughness is about 280% greater than that of a typical aerospace epoxy. So it's quite a high-performance polymer. The chemical ingredients that make this successful are these phosphites, phosphite inhibitors. We looked at a number of them, and what they are able to do is extend the pot life, where our team defined, there's a number of different ways to define pot life, but in our case, we're defining it as a gel point, where over to the left, of course, this is a liquid system, and then over to the right, it would be a gel system. And the amount of this phosphite inhibitor lets us tune where this gel point occurs. And so we can look at a plot of this pot life or gel point as a function of the inhibitor and catalyst concentrations. And what we found is that with these inhibitors, we're able to get over 30 hours of pot life in some systems, which enables us to do larger molds and structures. And as you'll see as I go through the talk, enables a lot of different things. The other thing that we discovered in this system is that with the use of these inhibitors, we have a lot of control over the rheological profile. And that control over the rheology really enables high fidelity in our manufacturing processes as well. And so by tuning the gel point with the amount of inhibitors, we have three different regimes here. Two are useful, but one is important to realize where it is. The first is what we call the liquid FROMP, or that's frontal ring opening metathesis polymerization. That means we're going to polymerize from the liquid, like in the test tube and the casting cell that I showed before. And this is very useful for resin infusion of composites. If we let it go beyond the gel point, this was actually a very surprising fact to us, that we can go beyond the gel point and there's still enough energy to frontally polymerize, and it enables us to process from the gel and do things like 3D printing and gel shaping into, as you see here. And then finally, if this goes too far, and it goes too far beyond the pot life, the gel will a background reaction will take over. It'll polymerize into an undesirable polymer, and you just don't have enough HR, heat of reaction, to propagate the front. So you want to stay away from that zone. Before I get into composites, I just wanted to show two examples of how we use this material to print. It also helps help you understand a little bit about how the front propagates. But as I said, if we tune this to work from the gel state and then chill it in a print head, we are able to 3D print. We use a heated print bed to trigger the front. And as you'll see, the front then is able to follow the print head, and we're able to cure in real time and basically 3D print on the fly. And so I'm going to show an example of a freeform 3D printing in air. And so this has been triggered on the heated print bed. And as this cycles up, you can see the front here chasing the print head as it goes through this freeform spiral. And everything behind the front is a cured thermoset polymer, again with a TG of 160. And it's just gel in that small segment close to the print head. You see this video will finish soon. And when it completes, you can see it's fully cured thermoset. There's no secondary curing necessary. I don't have time to discuss all the interesting rheology and different things that we're doing with printing for this presentation, but I picked one example and also just to show the layer by layer capabilities of using different nanofillers. And that's definitely an area that we're interested in and working and adding different nanofillers, carbon fillers, as well as even thinking about continuous carbon fibers. But in this case, I show an example of a layer by layer printing where we've added fumed silica nanoparticles to the DCPD. It also gives us another knob to tune the rheology. And you can see that we can create an ink with a very different viscosity. This one's gelled a little differently. And in here, we're just creating an annular structure, layer by layer. And this is a little bit different example, because instead of curing on the fly, in this case, we're just writing with the gel-based ink. And as you'll see, the frontal polymerization is going to be initiated ex situ. So there's our structure. There's the soldering iron in this video. And you can see it's just going to be touched there for a second. And this whole thing will now frontally polymerize after the fact. So in addition to, so that's a case where we're not using the heated print bed, we're polymerizing afterwards. We can also photothermally initiate these frontal polymerizations as well in our printing process. And it gives us the ability to make a lot of different types of structures and combinations of layer by layer and freeform printing as well. All right, so let me move on to the fiber reinforced composites manufacturing. And so, as I mentioned, this is going to happen from the liquid state. So we have a working time of several hours. And the way that we've chosen to make our composites in this initial work is using a resin infusion process. In particular, we're using a vacuum-assisted resin transfer molding process and infusing our DCPD monomer into woven fiber mats. In this case, it's a Toray twill carbon fabric. And basically, everything else, once you infuse the resin, it's very similar to a normal RTM process, except that we're just going to initiate this with a small heat trigger. The location of the trigger will vary, but we started out with the trigger on one side of the composite and let it move smoothly, the front propagate across the panel. So that's what I'll show first. So we start out with this single trigger processing configuration. And so there's a heat trigger, and then the resistive current is just turned on for a short while, and then the front propagates across the panel. And what I'm going to show you below in the video is an IR image where the IR camera is looking down on the panel. And this is a fairly good sized panel, a 10 by 20 centimeter panel. And you can see the current is on. That's just how we initiate it. The front starts moving across the panel, and we get this stable propagation as the exothermic reaction occurs. And we are able to fully cure this panel, as it says on the bottom, a 10 by 20 centimeter panel in just 2 minutes. Again, on a desktop with very simple tooling. We can make, we've made larger panels, we can make more complex shapes, and the volume fraction for this woven material is about 51%, very low void content. We've actually moved to a system that has no solvent in the resin system. And the TGs that we've gotten to are on the order approaching 160 degrees C as well for the TG of the composites. There are, so it looks like everything's working well in the video, but there is an important effect of adding fibers and other fillers to the frontal polymerization process, because every time you add filler, it is not reacting, it is not generating heat. So you're taking away monomer that is part of the heat that generates the heat necessary for processing. And so if we look at a plot of front velocity as a function of fiber volume fraction, you can see initially, here's our front velocities, initially as we increase the fiber volume fraction to say 20%, there's actually an increase in front velocity. And that's because the fibers are actually more conductive and let the front propagate more smoothly across the panel as we show. Then as you start to add more fibers and we get to a higher volume fraction material, that front starts to slow down again and can actually stall or in danger of stalling because, again, you have less monomer there. And so you have to be cognizant of that in your processing. Oops. Okay. All right. In addition, the maximum front temperature is coming down as I add more fibers because the front is less hot due to the heat dissipation. And that's also important. And There's a recent paper on this led by the Gubel group that actually were able to, again, predict these experimental trends quite well, and again, help us figure out numerically predict the processing windows that we need. All right. In order to get volume fractions up and address these issues with increasing fiber volume fraction, we thought a lot about how to modify the boundary conditions to get above to higher volume fractions. So our initial layout was, as I described before, that led to volume fractions about 52%. And we've done a lot of work to modify this using insulative plates. So the lamina is compacted between two insulator plates. And we actually also add some compaction pressure to our process. In the other prior example, we weren't doing any compaction. And it does two things. It minimizes the heat losses and increases the fiber content. You see we get a nice 62% volume fraction composite shown here. So the compaction step works quite well and is quite helpful for producing high quality composites. You can imagine as parts scale and get larger, there is you're asking a lot for a front to propagate meters. And so we looked at different alternate triggers to reduce the cure time and also the distance that the front propagates. We've studied two fronts, and this is two fronts in the plane. So as you can see, it's triggered from either end of the panel. They're going to meet in the center, and I'll play that video. You can see the current's on. It's triggered, then the current is off, and these two fronts will come together and merge. You'll see there's a bit of an exotherm when they merge. And this is something also that we have to manage and that we've looked at how to minimize the effects of a merging front. We have also looked at a through thickness cure. Let me stop that one. Where there is a heater at the bottom and it cures through the thickness of the material very rapidly. And in fact, this one cures the two front cures in half the time, as you might expect, of the one front. This one cures in about 30 seconds as we go through the thickness. And that's an exciting technique for more practical manufacturing. And if we compare these, really there is a bit of a trade-off between asking for a faster cure time, because we need to put a little more energy into, say, this through thickness case. And what I plot here is the cure time for each case, the one front, the two front, and the through thickness material. And you can see the cure time is coming down from 2 minutes to 1 minute to approximately 30 seconds to cure a panel, a composite. And then corresponding on the right-hand side is the energy input. So one front is the least amount of energy. It's a very small amount of energy, twice the energy for two fronts. And then, of course, to trigger it with this heater underneath it requires a little bit more energy, nothing close to an autoclave, but it's still significant compared to the other methods. And so we've gone from minutes to seconds in cure time, but at an energy penalty. We have also, in exploring this through thickness, we can do the through thickness process with some pressure and compaction. And that really leads to high quality composites and interesting methods of making multifunctional structures, as I'll talk about at the end of the talk. And I'm just going to show you some heat profiles. So here's our through thickness configuration where we've got the heater underneath the panel. The front's going to propagate in the Z direction here. And I'm going to show the profiles from two thermocouples. One's at the heater, one's at the top of the laminate, just to give you an idea how this works. And so basically, if there is no frontal polymerization and you turn the heater on, it's on for, in this case, about 40 seconds, and then it levels off as you turn it off. But you can see what happens when there is frontal polymerization. It's heating, and then all of a sudden we have that trigger where the exotherm kicks in, and you can see that very nicely here. And then if we're looking at, this is just the temperature at the bottom of the laminate. At the top, you can see this nice front that is propagating and moving through the material. And this through thickness technique with the compaction leads to some very nice materials. We can have very short trigger times and short cure times, again, about 30 seconds, and very high volume fractions, so 65% volume fraction, as I mentioned before. So if I go back to the Ashby plot I started with, and talking about reduced energy and time was our objective, with this frontal curing, we really achieved a number of different things. We were able to, with our 1 and 2 point initiations, really reduce the amount of energy per unit volume by several orders of magnitude, and significantly reduce the cure time for a panel. If we also did this little plot where we extrapolated to just different containers of resin, looking at the energy required. And again, this gives you this notion that it doesn't scale with volume in the same way that an autoclave cure does. And we extrapolated this all the way back. This is an extrapolated point for a 787 size container. And that's what lets us make this conjecture that, there's really a possibility of up to 10 orders of magnitude reduction in energy for a large structure like a 787 fuselage, and over 2 orders of magnitude reduction in the time it takes to cure such a size part. So a little bit moving on to the properties of these composites. Again, we compared our composites to conventional autoclave cured epoxy composites for the same weave and same volume fractions. And again, you can see this is the frontally polymerized system, an oven cured system, and then a similarly oven cured BPA epoxy. And the properties are slightly lower of the composite for the DCPD than the epoxy material. And this is an area of where we're continuing to try to improve. And there's been 2 things that we have been focused on and working on to improve properties. One is to increase the TG of our composites, get the glass transition temperature, basically get the cross-linking up, and also to improve the fiber matrix interface. These Toray fibers that we've been working with are largely optimized for epoxy systems, and we have been working on different fiber surface treatments to improve adhesion with dicyclopentadiene. And I'll just quickly touch on recent work in these areas. So the first thing are the increase in the glass transition temperature, and this work was just published last year. And what we stumbled into was working with these short chain esters, these norbornene-based crosslinkers, by adding different concentrations of this crosslinker into our DCPD resin. You can see by these DMA curves that we can clearly the rubbery modulus is changing quite a bit, as well as the glass transition temperature, indicating that we're getting increased cross-linking. And as you can look from the peaks in the tan delta, that we're pushing the TG out from about 160 C without any crosslinker to at the highest concentrations of crosslinker up to 220 degrees C. And that actually, I think, is quite remarkable that we're getting a 220 glass transition temperature, again, on a desktop with very simple molding and very small amounts of energy input. Again, the amount of crosslinker, of course, is also affecting the mechanical properties, so the ductility of the polymer is going down, but it's still pretty tough. Yield strength is going up with crosslinking, and elastic modulus is also going up with crosslinking, as you might expect of the neat resin. We've also incorporated, so just to summarize that quickly, these ester-based crosslinkers have a minimal effect on front velocity, which was an important element of this study, because everything you add to the system could take away from the frontal polymerization process. And we are able to get these high TGs and increases in stiffness and yield. We then incorporated the short chain ester into a composite, which was no small feat since we're synthesizing this all here at U of I. But again, we chose to go with the through thickness curing method. And you can see, again, the DMA summarized for the composite on the right-hand side, that by increasing the amount of cross-linking agent, we get our changes in glass transition temperature of the composite. And so we're able to push up our TG of the composite from 150 and approximately 155, 158, all the way up to about 170 for the composite. So the increase isn't as significant as for the neat resin. And that's a really interesting question that we're still trying to figure out why we're not seeing quite the same increase in TG in the composite system, and an area of ongoing research. Also ongoing, and again, I'll just mention this because we're doing a lot of testing, and it is a challenging problem. We have been working on functionalizing the fiber surface in order to optimize the bonding of the DCPD to commercially available fibers. And we've looked at several different fiber surface treatments. Initially, this norbornene dicarbonyl chloride is perhaps the most promising, and basically ongoing work, as well as we look and characterize the interface over a large number of samples and work to scale that up to our woven composites. All right. So what I'd like to finish with is how we use these manufacturing techniques. Clearly, they can be used for, or there's real promise for fiber reinforced composite manufacturing. But as many people know, our team is very interested in multifunctional response and imparting things like self-healing and other types of responses. And one of the methods that we do that is by putting a vascular network into a composite structures. And multifunctional vascular composites can do many things. Basically healing and regeneration of damage. So we've made self-healing structures. We've made self-cooling composites. Here you see an image of just one of these cooling channels in a complex curved corrugated composite structure. And we've used them for electromagnetic reconfiguration as well, where we're running a conductive fluid. So the functionality depends a lot what fluid you're running through the vascular network. Now, we've spent a number of years pioneering different techniques to make these vascular networks. This is a technique that we actually worked on with Jennifer Lewis's group, where we started out just making using ink scaffolds that were 3D printed. That sacrificial ink was then polymerized in a polymer matrix. You heat it, you get rid of the ink, and you can get pretty complex vascular networks in polymer components, and they're relatively small. There's a lot to this process. And we quickly realized that it was limited, especially towards aerospace grade composites, that the sacrificial inks just wouldn't survive in a composite and hold their structure. Then we moved on to this process we lovingly called VASC, which is vaporization of sacrificial components, where we did a lot of work on developing sacrificial polymer templates that would be embedded in the polymer that can survive the cure cycle and then go through a second heat cycle to vaporize the material and leave the architecture that you want in forms of empty channels or networks. Just to say a little bit about this process some more, we start out with a sacrificial polymer. In general, that polymer was polylactic acid, PLA, and we cure it in. And it survives the cure cycle, but then it needs a post-cure cycle to get rid of the sacrificial template, and ideally it vaporizes. And the vascularization temperature for some of our prior materials was about 200 C. I'll say a little bit about the timing on that. But when you're done, you get these beautiful microchannels in the polymer or the composite. And so some of our early work, this is just one of those cured composites. And over on the right here, I show PLA, a glass epoxy composite with PLA fibers that are undulating with the undulation of the weave. Some of the weave fibers have been replaced, the 3D weave been replaced with these sacrificial fibers. And what we wind up with is this beautiful composite with vascular channels. But to make this composite on the bottom, we had to go through the conventional cure cycle. So this, in this case, was an 8-hour cure cycle. And then what we called a VASC post-cure, which actually took up to 16 hours at 200 C. So it took, while it was quite successful, we weren't worrying about the energy it took to do this, all right? And it has some limitations, as you can imagine, as you're trying to get something to go through a cure cycle like that. So as we got started with our frontal polymerization process, we asked this question, can the thermal wave during frontal polymerization, we've got a lot of energy there. Sometimes there's quite a bit of excess energy depending on the monomer and the boundary conditions, but can that initiate vascularization? Can you have simultaneous polymerization and depolymerization, polymerization of the monomer and depolymerization of the sacrificial template? So this is a snapshot from a thermocouple of what the temperature profile looks like as that wave propagates through a polymer. In this case, the Tmax is at 185, and we have about 100 C drop in 3 minutes. So really, this is the conditions we have to depolymerize a sacrificial template in the way that we've done before. If we're going to use the frontal wave, the current postdoc and former PhD student Mayank Garg stumbled into this really interesting low temperature sacrificial polymer, polypropylene carbonate, that's been dosed with a photo acid generator, and it is able to degrade at fairly low temperatures. In fact, roughly around 90 degrees C, which was perfect for our application, and it's able to do it fairly rapidly at those temperatures. So we are able to process, and as this goes, I should mention, this goes from a polymer, PPC, to its monomer, propylene carbonate. And because this is a thermoplastic, it's also very easy to 3D print, as you'll see, and also very useful. But here it's been pulled into fibers. We've got the fiber. This fiber is actually quite round with good fidelity, but as we look down on it, it's embedded in DCPD monomer. It's going to be triggered from left to right. And what you'll see is the polymerization front and the depolymerization fronts moving right here. So there's the polymerization front, and there's the depolymerization front lagging behind as the material on the outside is going from monomer to polymer, and the material on the inside is going from polymer to monomer and evacuating so that we get nice open channels in our DCPD. We can look at them under micro CT. They actually really have nice fidelity. We are able to extend this into more complex networks where we 3D print the sacrificial template, embed it in, and then vascularize it using the frontal polymerization. And so this, the design process, in this case, we started from, as an example, for a leaf. We digitize the leaf and parse it into G-code, create our sacrificial template. And this is what that template looks like embedded in our DCPD monomer. And again, the front is going to go from left to right, and you're going to see this polymerization process of the outside polymer material and the simultaneous depolymerization of the template in this fairly complex architecture. And it's just a fun video to watch. And what we are left with after this is evacuated out, and usually we just rinse the channels a little bit to get rid of any residual monomer, is our leaf-like structure that we're able to create quite rapidly without the use of a high-temperature oven. And this work just appeared 2 weeks ago in Nature Communications, and so there's a lot of details of the process in that. What I'd like to finish with, though, is just we've been able to extend this process from the pure polymer to the composite. And so we're able to do this rapid, essentially one-step or tandem manufacturing of vascular composites. So we put basically our PPC fiber in. Again, we're going to rely on the through thickness cure to evacuate these in a composite. And we're quite successful, even though the reaction temperatures in the composite are somewhat lower than in the neat resin, the maximum front temperature. But you can see that we've fully evacuated a vascular channel in this woven composite. Looks good. You notice the example I'm showing here is a fairly low volume fraction fiber reinforcement. That goes back to this notion: as I add more fibers, I lose heat. But in the end, we're able to reduce this cure and vast time down to roughly 30 seconds from over almost a 2-day process from before. It's 10,000 times less energy and 1,000 times faster. So that's a good result. And we've been working on this issue of the effect of the carbon volume fraction. Again, Philippe's group has been doing the modeling, and we're able through this compaction process and keeping insulating plates, we've made it all the way to 50% volume fraction, and we're pushing forward. There's work in progress right now to push on and get these higher volume fractions and also go to more complex networks. So I have a summary slide there that, basically frontal polymerization enables rapid processing of composites. Through the use of these inhibitors, we can form fairly complex components and parts, either from liquid or gel state. We've gotten high TG carbon fiber composites in relatively short times with low energy. And we've demonstrated a method to make multifunctional structures like this. One of the things that we're interested in doing for the future, we're looking towards like ways of upcycling composites too, because as we know, many of these materials are high performance thermosets. We already discussed the high energy costs and slow cure times, but yet these materials, they need high temperature stability, high strength and stiffness. That's great for their service life, but then at end of life, they're in a landfill. That's a now famous image of all these wind turbine blades in the landfill. And so we've been thinking, through this talk, I've told you about a method to reduce the energy costs of the fabrication process. And what we're working on is an interesting methods of ways of upcycling this. There's been some beautiful work by Jeremiah Johnson's group at MIT on bringing in cleavable units. And we've been collaborating with that group to incorporate cleavable units in our frontally polymerized system. And our hope is to be able to have upcycling, to be able to cleave these monomers and be able to recover and upcycle those into usable products. So that's sort of what we're thinking about for the future with these tools as well. So let me end there. I'm a little over, I think, and hopefully leave some time for some questions, and just want to acknowledge the amazing group of graduate students, postdocs, and faculty that I work with here at the University of Illinois.
Professor Sottos, thank you very much. On behalf of all of us here at Purdue putting this on, and all the audience, thank you very much. And happy to ask a few questions from those that are asking. One of the first questions I'll ask here is, what are the scale-up issues in this? That question is appeared. What are the scale-up issues, particularly for larger, complex structures as you're targeting aerospace kinds of structures?
Yeah. So I would say the first thing I should mention, and my colleague Jeff almost always says this in his talks, is that the chemistry that we're using is almost all off the shelf, right? So everything, save a few of the cross-linkers that I talked about towards the end, are available in large quantities. There are resin suppliers that have these materials, so that's a good thing for scale up, and also more advanced formulations of DCPD for composites. In terms of making large parts, I think it's the same things that I discussed here and that plague many systems, right? Once you start getting into large molds like a wind blade structure, you're really going to have to think about how you want this front to move. If you want it to go through the thickness, that seems like a very clever way to do a large part. If you want to have multiple fronts, but then you have to manage where the fronts meet, like any polymer manufacturing process. So I think managing and being able to predict how the fronts move for a given set of boundary conditions. And so it will rely, your tooling may look a little different than for a traditional composite, because it's actually you're looking to keep heat in. The tooling also needs a lot less requirements because, again, there's not a lot of heat and pressure going on in these systems.
Thank you. There are some questions about residual stress that maybe are along the same lines of that, but residual stress, I know you commented others are doing the modeling, but can you comment on residual stress development, particularly in the composite parts fabricated with this method?
So the interesting thing is that the residual stress development is quite a bit different than the residual stress in an autoclave composite. In an autoclave, everything is constrained, and as you start cooling it down from its, from a place where there's very little residual stress, and you start cooling down, it's got heavy tooling. Everything's, in particular, the inner layers of the composite tend to be constrained, and you get residual stress development. You can have spring back and all sorts of other things. In the components that we've been working with, depending on how the front is moving, there's always an open free surface of monomer as this front moves through. And in our works to date, although we have not quantified residual stress in as formal a way as has been done for aerospace composites, the anecdotal evidence is that there is very little residual stress in the final parts because of the way this front is moving. The biggest issue that we come into is when the two fronts meet, and there actually can be movement of material and flow as those two fronts are meeting that needs to be mitigated. And then if you mitigate it, then there could be residual stress development at just the seams, is where we've most seen it.
Thank you. Some questions also about practical limits on thickness, or if there are fiber types that you've played with between glass, carbon, and other fibers, and perhaps anything on surface treatment of fibers that you may have looked into.
So we have worked with both carbon and glass. Carbon has been the dominant fiber that we work with, but we have explored glass both computationally and a few experiments with it. So both are possible. In terms of thickness, there isn't a lot of limitations on thickness of these materials. They will frontally polymerize, and in fact, thickness definitely encourages a stable front propagation in these materials. They don't have this runaway exotherm problem that we've seen because the front is moving in this very stable and controlled fashion. And in fact, it's kind of interesting. The ideas for this really came out of some early work that Scott White did on cure fronts back in the early 90s, when thick composites were a very sought after research topic. And this notion of pushing a cure front started at those very early seeds. So as a way to mitigate the exotherms associated with thick material. So we haven't done a huge amount of thick material, but you can basically, I said, we've done like a liter container of resin, and that cures up just fine with a single trigger without a massive exotherm. In terms of surface functionalization, we've been talking to some different groups. There's a lot of work going on with DCPD composites in the U.S. Army because of their toughness and resistant to projectiles. And there's been a lot of efforts there on the glass DCPD interface. There's also quite a bit of proprietary work on glass DCPD interfaces. And then a few groups, some in Australia, that have been working on the carbon fiber interface. And so there is, and I just showed the three strategies that we've looked at so far for surface functionalization. And that's about where we are now. There's the way the interface forms in these materials is quite a bit different than a thermosetting system, and that's of interest to us as well. We're also hoping that in tandem with the work that's going on as part of our NSF program, there's a lot of machine learning of monomers, and we're hoping to also bring in more about how to capture what's going on and model at the interface a little bit more using these tools as well. So I think the interface problem, as always, is a rich problem to study.
Well, thank you. Thank you again. Thank you for the answers. Thank you for the presentation. Again, we thank the audience. And today we'll conclude the first in the series of Global Composites Experts webinars. We will begin the second series again in the fall. Watch your email as we'll be sending out reminders for those as they kick off. And again, certainly visit the cdmhub.org site for more questions and answers. Again, Professor Sottos, we thank you very, very much and wish all a good day. Thank you.